السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Today, inshallah, we will begin covering the topics that we have to cover after midterm. So we will start according to our course semester plan from chapter 5, mechanical sensors. So we have especially the strain gauges, the strain sensors, which is in section 5.3. So we have here, we can define the strain. What is this? The stress. The stress is the forces applied to an object, like for example, pressure, which is actually force divided by area, and the stress is the same as the pressure. Also, if you need to measure a weight for a human being or any object, then you actually the weight is a type of force. So it is a force, and we can use this or these strain sensors, strain gauge sensors, to measure any type of force, like weight, for example. So again, what is the meaning of strain? Strain is the result or deformation of a stress. For example, if we have a metal rod here with a cross-sectional area A and a length L, if we apply a force in this direction, then this will cause a strain, and the type of this stress or the strain here in this case is tensile, because due to the force here, the length will be increased by a certain amount, usually small amount. So L in this case is equal to, say, is equal to L here is equal to L0 plus delta L, because this is tensile stress. On the other hand, we have this rod has an applied force in the opposite direction. So we have, in this case, a compressional. We have a compressional stress strain. In this case, the length, because of the compression, the length will be decreased. So L equal to L0 minus delta L. Okay, so we have two types of stress strain. We have tensile, the length increasing, and for compressional, the length is decreasing. So again, this is the stress formula. It is a force divided by area. So we have the unit of force is in Newton in a SI system. The unit of area is the meter square. So force divided by area means that the unit is Newton divided by meter square. Newton divided by meter square. The strain is actually is the measure of the change in length. So it is actually delta L over L. Delta L is the change in length in meter. L is the original length. So delta L over L. And you can notice from this that this is unitless quantity. Unitless quantity means doesn't have unit. This is unitless quantity. Okay. So, but generally speaking, the practice between engineers, scientists, they put a unit for the strains. Say, for example, if we have a strain of 100 or 1000 micro, instead of putting it like this without unit, we usually the practice is to put unit, for example, meter per meter or inch per inch. So we know that there will be cancelled, but we can, this way of expressing the strain is more understandable and more clear, because when you say 1000 micrometer, this is the change in length. This is delta L, and per meter, which is the length of the rod or wire. So we have 1000 micrometer per 1 meter of length. We have 2 meter length, then we have to multiply this by 2. Okay. Now we see that the cause of this stress, the cause of this stress is the application of force or the stress. Sorry, the cause of strain here is the application of force or stress. So the stress and the strain, they are related to each other. And next slide, okay, explain the relation through a graph. So we have this graph. This is the strain here, and this is the stress. So we have initially we have a straight line. This straight line, it is a linear curve, or it is a linear region here. So as we increase the stress, the strain is increasing also up to certain point. This point is called nicking. So we have after that the curve here is not linear or non-linear. This curve here is non-linear. Okay, and we can, in other terms, say that the first part of the curve, which is linear region, we can call it the elastic region. So the region here is the elastic region. This is the elastic region, and here the non-elastic region. This one is the non-elastic region. Elastic mean, it comes from elasticity. That means that if you elongate a rod or wire by applying force, then the length will increase. If you remove the stress, then the rod will return to its original length or shape. This is called elasticity. But this is up to certain point. If you increase the stress more and more, and you exceed, you are working beyond the nicking point, in the nonlinear region, in the non-elastic region, then if you remove the stress, then the rod will not return to its original length and shape. There will be permanent deformation, permanent nicking. And nicking, maybe we can describe it like this. We have this rod here, then because of nicking, you see this type of nick like this. So this is the nicking. As you increase the stress more and more, the nicking will become larger. And if you remove the stress in this region, the nicking will be permanent, will not be removed. Okay, so it will be permanent deformation. And usually strain sensors are working in the linear region to preserve the material characteristic. Okay. And we have the slope of this curve in the linear region. The slope actually is stress over strain. Stress over strain over stress. But we have here the E, which is called modulus of elasticity, or Young's modulus, is equal to stress over strain. So the slope in this case is 1 over E. Is 1 over E, and E has a unit of Newton per meter square because has the same unit as stress, because strain, as you know, doesn't have any unit. So this is the stress strain curve. If you continue to increase the stress, you will reach this region. At this region, the rod will break. It will be divided maybe 2 parts or more. So now, as you know, the resistance in any wire is equal to rho L over A. L is the length, A0 is the original A, and L0 is the original length. R is the resistivity. And this is, you should know it from physics or from circuit 1. So this is the fundamental relation between resistance and length and area. As we increase the stress, we increase the strain, means that increasing the length. Increasing the length here, the area will be decreased to preserve the volume. The volume should be of the rod should be constant. So the original volume is equal to L0 times A0. This is the original volume. And the resulting volume should be kept constant, same as the original volume. So this volume should equal to this volume. The new volume is equal to L0 plus delta L, the resulting L, times the resulting area, which is A0 minus delta A. Here, the length is increasing, the area is decreasing, but keeping the volume constant. Okay. And R, the resistance, is equal to R times L0 plus delta L divided by A0 minus delta A. If we substitute this equation in this equation, or this equation in this equation, we'll have a new equation, this one. And after approximation, because this equation is nonlinear, both actually this equation and this equation is not linear. But when we substitute this one and this one, when we made the approximation for small changes, we need ignore the small changes, for example. Then we have this approximation, this equation, which is says that delta R is approximately equal to 2R0 times the strain. This is the strain. This is the strain. Okay. And this is very important formula. We will see it next slide, inshallah. So after solving this example. This example here, we have R0, the original resistance of the strain gauge is equal to 120 ohms. We need to study the strain effect in changing resistance as well as the temperature effect. And we will compare both effects. Okay. Temperature effect here in this case is undesirable. We need to cancel the effect. We need to compensate for this effect. We need only to measure the strain. So we need only the effect of changing the resistance due to the strain only, not temperature. So we'll compare first the both effects. Suppose that we have the delta R change in resistance due to strain is this equation. Delta R due to temperature changes, we will use this equation. So for the strain, delta R is equal to 2 times 120, this one. This is 220 ohm times the strain, which is 1000 micro. So times 1000 micro. If you multiply this, you will get this result. Only we have change of 0.24 ohms. This is due to the strain. While the change in resistance due to temperature, and we will have, if we substitute the value of alpha here in this equation, then we will get delta R equal to 0.48 ohm per degree Celsius. So if we have only change by 1 degree Celsius, then we have only 0.48 ohm. If we have 2 degrees, then we have to multiply by 2. So if we compare this delta R with this delta R, we see that the change in resistance due to temperature will be double the value of the change in resistance due to the strain. And this is undesirable. So you will get, for example, if you add this to this, you will get a change in resistance of 0.6 or 0.72 ohm. But this is actually this strain change only is 0.24, and you got this one. you will have wrong result. Means that the change in resistance due to temperature mask the result. You will not know the actual strain in this case. So we need some type of compensation of to remove or to reduce or to cancel this temperature effect. We need only the change in resistance due to strain, because we are using the strain gauge to measure the strain, not to measure the temperature. Okay. So we have this formula. The gauge factor here is equal to delta R over strain. And this is the same as we solved the previous example, delta R. We say that delta R is equal to 2 R times delta L over L. So delta R, if you bring this R here, so delta R over R is equal to 2 delta L over L. So this 2 is the gauge factor. This 2 is the gauge factor, and it is around 2. Usually it is around 2 for metals. For metals, usually this is around 2. Okay. And for special alloys and carbon, maybe the gauge factor will be 10. So again, the general formula for gauge factor is delta R over delta L. If you bring this one here, so you are dividing delta R over R by delta L over L, you get here 2 for metal. This is the strain gauge. And the strain gauge here is very important factor, because it describes how the strain gauge is sensitive. We have more gauge factor, larger or large gauge factor, we have more sensitivity. We will get more delta R, more changes in resistance for the same strain. So it is called, it describes the sensitivity of the strain gauge. Now we will look about the construction of a strain gauge. The strain gauge usually consists of a thin metal here, like this one. You see, this is thin metal. It is coiled like this in a zigzag fashion to increase the length, because increasing the length means increasing the sensitivity. So this is the sensitive direction, this one. If you apply force in this direction, then this will be elongated by a certain amount. Also this one, also this one, also this one. So we have multiple wires. So the length is changing, will be changed for this one and this one. So multiple changes. So the sensitivity for the zigzag pattern will be more. This metal or thin foil, okay, is bagged or glued on a backing. This is the backing here. The strain sensor or the strain wire is bagged or glued on the backing by a certain type of glue with end points. This end point, this is solder pads. You need to connect external wires, for example, and we will see how to connect this in Wheatstone bridge as a signal conditioning circuit. So this direction is a sensitive direction. This direction is insensitive. You apply force in this direction, then this will not be sensitive, because only you are changing the diameter here, and this is very small. You have multiple diameter change, and usually you can neglect the change. You will not observe these very small changes, but in this direction you will see the change very clearly. Okay, especially when you connect it to a Wheatstone bridge. Okay, this is the construction of the strain gauge. So strain gauge actually is a sensor that uses the change in resistance as a measure of the strain. Because of the strain change, as you increase the stress, you increase the strain, means you increase the length, means you increase the resistance. When you put it in the Wheatstone bridge, this increase in resistance will cause an increase in voltage at the output of the Wheatstone bridge, as we will see, inshallah. Okay, this is the Wheatstone bridge here. Okay, this is the signal conditioning. In this case, for example, we have we put here two strain gauges, one in the sensitive direction, this one, in the sensitive direction. The other one is in insensitive direction. It is called dummy. So this one is active strain gauge and this one is dummy strain gauge. So the first strain gauge, the active one, we put it here in the Wheatstone bridge. The dummy strain gauge, we put it here in the opposite branch of the Wheatstone bridge. So this Wheatstone bridge, we have this excitation voltage Vs, we have this resistance, we have this resistance. Usually we use resistances to be equal, so R1 usually equal to R2 and equal to RA, the active strain gauge, and it is equal to R of the dummy. So initially the bridge is balanced, so the voltage here VB at this point is equal to the voltage at A, which is VA, and there's no voltage difference. The voltage here, V out or delta V here, is equal to 0 initially. But if you apply force, then this will increase in its resistance, so VB will increase. But VA will kept constant, no increase. VA is equal to Vs over 2, because this resistance is equal to this resistance. So the voltage here will be equal to Vs over 2. VA is equal to Vs over 2. Nothing changing for VA. Only the change happens to VB because the change will, due to the force, will happen here in the active strain gauge. The dummy strain gauge will not change its resistance due to strain. So what is the benefit for the dummy here? As we said before, we need temperature compensation. Temperature compensation here, because we use two strain gauges, one active, one dummy. If the temperature changes, then this will increase due to this temperature, and also this one will increase with the same amount because they are near each other. They are in the same environment. So the temperature effect will be the same. So this change in resistance due to temperature will equal to this change in resistance due to temperature, and the effect will be cancelled. Only the change in length due to the force will be active here in the active strain gauge. So VB increasing, VAA is constant. Here, this is the derivation. You can see this RA is equal to R times 1 plus delta R over R. We have delta V, which is VA. This is VA minus VB, or VB minus VA. Sorry, it is because it is in minus, so it is VA. It is VA minus VB. VA minus VB, so it is in minus because usually VB is larger. This increasing, this kept constant. So VB is larger than VA, so this is negative here. After approximation, we can get delta V is equal to this Vs, the excitation voltage, times delta R over 4. If we substitute delta R over R by its equivalent, we know that delta R over R is equal to this value, gauge factor, times delta L over L. We will get this equation, delta V equals approximately minus Vs over 4, gauge factor delta L over L. And this is called quarter. This is called quarter quarter bridge or 1/4 bridge. This is called quarter bridge. For quarter bridge, we use only one active string gauge. One active string gauge. The other gauge only for temperature compensation. It is called dummy. So if we use one active string gauge, then we have quarter bridge, and the relation for the output voltage of the Wheatstone bridge is this, divided by 4. Vs, the excitation table voltage, is divided by 4. We will see another example now, another case where that we use two strain gauges that are active here, one on the top of the beam. This is the beam, cantilever beam, fixed on this wall, and here we have an applied force. We need, because of this force, the cantilever beam will bend, so the top strain gauge, which is the active one, will extend its length. So we have change in resistance. This one is R0 plus delta R, but the active gauge, which is in the bottom of the beam, will decrease its length because there is compression here. So the resistance here is R0 minus delta R. And the dummy kept constant R0, and here is also kept constant R0. So we have 4 strain gauges, 2 active and 2 dummies. So the first active here, and the second active is here. Here the dummy, and here also the dummy. Initially, all 4 gauges are equal in resistance, and we have 0 voltage, because VA is equal to VB. VA is equal to VS over 2, and VB is equal VS over 2. This is VA, and also it is VB. This is initially only. Initially. Okay, initially. If we apply a strain or force like this one, we have this strain gauge A1 will increase. This one will increase its resistance. This one, because it is in the bottom, will decrease in its resistance. So VA and VB are changing. VA is increasing in voltage, VB is decreasing. So we have more sensitivity. If we derive the equation will be like this. Now delta V, which is here, the output of the Wheatstone bridge, is equal to minus Vs over 2 gauge factor times delta L over L, which is the strain. Here we are dividing by 2. Before, in the quarters gauge, we divide by 4. Now we dividing by 2. So this voltage is larger, is double what we have from the quarter. This bridge in this case is called half bridge. Half bridge. Half bridge. In this, where we have used two active strain gauges. We have used 2 active strain gauges. This one and this one. We have half a bridge, and we divide the output here by 2. So we have double compared to the quarter one. Now we can use the same here. We can, instead of using 2 actives and 2 dummies, we can use all active. So 2 actives on the top, 2 actives on the bottom. So in this case, here the first active, this is the second active, here the third active, and here the fourth active. If we use this, then we will get more sensitivity. More sensitivity with temperature compensation. With temperature compensation. Okay. In this case, delta V will equal to, for full bridge, delta V is equal to Vs, okay, minus Vs delta gauge factor delta L over L, without any division. This is, we divide by 1 here for full. For full we divide. This is for full bridge. Okay. For full bridge we divide by 1. For half a bridge we divide by 2. For quarter bridge, we divide by 4. Okay, so the largest sensitivity is with when we use the full bridge. Full bridge means we use the 4 string gauges as active string gauges. What is the difference between active and dummy? The active, we fix it or glue it on the beam in the sensitive direction, while the dummy, we glue it or fix it on the beam, maybe either on the top or the bottom, in the insensitive direction. So in this case, only it will change its resistance due to temperature, not the force. Uh, we said that before, that the strain gauge for the gauge factor, sorry, for metals is around 2. For some alloys is around 10. For semiconductors, we have the gauge factor here is very is large, maybe 50 or 200, and it is negative. So we have more the strain gauge sensors, the semiconductor strain gauge sensor are very sensitive. They are negative. They have negative strain or gauge factor. Now we have the load cell. What is the load cell? The load cell actually consists of a beam or a yoke metal body, and on the metal body we usually glue some strain gauges. In this case, we use this one as, for example, dummy, this one as active, and from the other face, the other direction here, we put another 2, because this is 3D. Okay. Okay, so in the other direction we have also. So in total we have 4 strain gauges. Either we can use 2 active and 2 dummy, or 4 or active. 4 active, much better in sensitivity. So if we put this one, this load cell in this direction like this, for example, okay, and we apply force here, and this on the ground, and here the strain gauge sensors, okay. Then this is the compression force. Then the length of the active strain gauge will, okay, this one, sorry, will increase. So the load cell mainly used to measure weight. Usually used to measure weight, and also this the same signal conditioning is the Wheatstone bridge. Most of the time the Wheatstone bridge is built in with the load cell. So all or most electronic weighing instruments, they use this load cell in order to measure the weight. For example, if you have weighing machine like this to measure your weight, and this is digital readout here. Then we have usually strain gauge here, we have strain gauge here, we have strain gauge here, and we have strain gauge here. Sorry, load cells. So we have 4 load cells. And the reading here, it reads the average of these 4 load cells, divided by 4, okay, to be more accurate. We will stop at this point. We will, inshallah, have another video to solve some examples regarding the this strain gauge.